Hey everybody. So I'm going to do an example in this video of finding the space curve, or I'm going to find the vector function associated to the space curve made by the intersection of these two surfaces. So we've got x plus y plus z equals 7/4 and z equals x squared plus y squared. So let's just get a quick idea of what these things look like. We should recognize x plus y plus z equals 7/4 as a plane. It's linear in x, y, and z. And then this one, we could maybe think through some traces really quick. I'm not going to spend a ton of time. It's not necessarily going to be necessary for the problem, but it's always nice to get a look at these things. So remember what I do with traces. What we do with traces, we can think of fixing one of the variables, right? And I'm going to choose to fix z in this case. And understanding what happens for each value of z to get a picture of this equation. So for instance, if z was equal to 0, the only solution to this equation is x squared plus y squared equals 0 is only if they're both 0, right? It's also clear z can't be negative numbers because we can't add two square numbers together. And so if I put in positive values of z, like z equals 1, we get x squared plus y squared equals 1, which means that if we just look at whatever this surface is, if we slice it with the plane z equals 1, the slice looks like a circle, right? If I look at z equals 4, it looks like a circle with a radius of 2. And if I look at z equals 9, it looks like a circle with a radius of 3. And so what I'm seeing is I get this shape that's making bigger and bigger. You know, if you take slices, like imagine a bowl, if you slice it, you get circles as you go up. So each of these circles represents a higher value of z. So if I were to try to sketch this thing, right? Oops, there's my x, y, and z, right? It's going to be something like and I can imagine making it three-dimensional, right? There's those circles. For each value of z, we get a larger and larger circle. So that kind of gives us an idea. It's like a bowl shape, right? And then there's a plane that's going to be slicing through it. In reality, it could be a plane just touching it at one point. Something we'll come to know as the tangent plane that will show up when we go to figure out this curve. But I'm going to kind of draw the most general idea that it's going to intersect in like a slice. And if you could imagine it coming at it at an angle, right, we'll get some kind of ellipse shape in that angle, right? It might be a little hard to picture. We'll do a better job later, but just get an idea of what we're going for here. So I did a previous video on doing this, and I had a much easier time. This is a little bit more difficult of a problem. So let's think for a minute what it means for a point to be on what I'm calling this curve of intersection. What it means is that it's a point on both of these surfaces. What does it mean to be a point on both of these surfaces? It means that it satisfies the x, y, and z coordinates of whatever points we're talking about. All of these points satisfy both equations. So for any point on this line, it must be the case that x plus y plus z equals 7/4. And at the same time, those same three coordinates must abide by this relationship. So at these points, and nowhere else, both of these are true, which means I can substitute z equals x squared plus y squared into this equation, right? Because at these points, z has to be equal to x squared plus y squared, right? If we pick some other points on the plane, all it has to satisfy is the original plane equation. But by insisting it also lie on this other surface, z has to be equal to the sum of the squares of the other two components at the same time that this is true. So that's where we get this equation. So let's do a little bit of algebra to this equation, right? And you might notice something about this equation right now. Maybe you don't. This is the kind of thing that I don't know if I can make a rule to say when you do this, but I'm noticing a pattern that I've got quadratics in both x and y. And at this point, this is just something to try and see what happens. So what I'm going to try is completing the square for both of these quadratics, right? So remember with completing the square. So I'm just looking at the x squared plus x right now. The coefficient of x is 1. To complete the square, I take half of it and square it. So half of 1 is 1/2, squared is 1/4. I'm going to do the same thing right here, but I've got to add the same thing to the other side. Okay, so what do we get? Why did I do that? Well, because this can now be factored into x plus 1/2 squared. This can now be factored into y plus 1/2 squared. And now on this side, I've got 9/2. Okay, now, is this useful? Well, one thing this tells us is that if I were to, taking this shape in my little drawing here, if I were to take a light, right, if I shined a light from above onto this thing, the shadow that this shape would create would be, so my picture's not totally accurate, but the shadow this thing would create would be a circle whose center I can read from this equation. So in other words, I'm ignoring the z component. I'm just seeing now that these points, because z is related to both x and y, give me a way to kind of connect all of them by just using x and y. The relationship between every point on this intersection is that it's above a point on this circle in the xy plane given by this equation. And this equation is a circle with radius, oops, sorry, this is a little error here. That 2 should have been a 4. So that should be 9/4, right? Just adding what's up there. So the radius then, of course, is the square root of 9/4, and the center is -1/2, -1/2, right? Remember the equation of a circle, x minus h squared plus y minus k squared equals r squared. So since they're both positive, they must have been negative, must be a negative center, right? So that's what the shadow of this shape looks like, okay? In other words, another way to think about it is this cylinder, this represents a cylinder, this equation here, right? This drawing might get a little bit messy. Let's just do it again. I've now got this cylinder. So here's -1/2 would actually be back behind there somewhere, and there's a circle, right? Something like this. Well, it's a cylinder. If I ignore, if z doesn't show up in the equation, then z can be anything. So we can extend this cylinder in the vertical direction, and this curve that we're after, that I drew up here, is going to live on that cylinder. Okay, that's the idea. So there's a couple different ways we can think about it, but in either case, what it means is if we can parameterize this circle, then we're good. Well, we know something about parameterizing a circle. So I'm just gonna use parametric equations for a moment. Eventually we're gonna make a vector function. But I know that if I do cosine of t and y equals sine of t, I get a circle with radius 1 centered at the origin. So I need to stretch that circle out so I can increase the radius to 3/2. And then I need to move all of my coordinates, right? If my original circle is centered at the origin, I want to move, right? So here's a circle. I want its new center, right, to be over there. I need to move every point, that far down, right? I need to move every point a half a unit to the left and a half a unit down. Well, that's really easy to do. I just subtract 1/2 from both of these, and I've moved that whole circle a half of unit over, which means the center is now at half a unit to the left and half a unit down. And so this gives me my parameterization for X and Y. All right. Now it's simple enough to get Z because I already have Z in terms of X and Y. We just take X and square it and add to that Y squared. Right? And certainly we could do some algebra on this thing. Yeah, let's see what happens. I didn't do it before, but let's see what happens. It might simplify nicely. This is perfectly valid, but as long as we're here, let's just do it. So if I square this thing, I'm going to get 9/4 cosine squared t. I'm going to get minus 3/2 cosine t. I'm going to get plus 1/4. Just make sure, yeah, that's right. And then I'll get almost the same thing here. I'll get 9/4 sine squared t minus 3/2 sine t plus 1/4, which is equal to, well, the 9/4 cosine squared plus 9/4 sine squared gives me 9/4. I've got 1/4 and 1/4, so I'm going to get 2/4. And then I've got minus 3/2 cosine t plus sine t. Yeah, maybe this is a little nicer. You can combine this to be 11/4. Not much happened. I thought maybe a little more would cancel or something like that. In any event, this is a nice parameterization, and we can write our vector function just taking these to be the component functions. So the vector function for this space curve would be r of t. I'm going to need a little more space. Let me just move something out of the way here. We'll have r of t is equal to, so what have I got? 3/2 cosine of t minus 1/2, 3/2 sine of t minus 1/2, and then 3/2 cosine t minus 1/2 squared plus 3/2 sine of t minus 1/2 squared, close brackets. And that's our vector function for this space curve here, right? Again, remember the difference when we think about the parameterization. I can say something like, I can take t to be 0 to 2 pi. If you do any more than an interval of 2 pi, it's sort of describing something that keeps spinning around, which you may want. So this is kind of arbitrary what I've chosen here. I have to have at least a 2 pi interval to make sure I cover the whole curve. I could just make it all real numbers, and it just represents a particle going around and around and around. This function, the vector function, remember, is representing or is spitting out vectors that for each value of t are pointing at a different point on this surface, okay? So let's take a look at this graph better than my scraggly drawings for a second. So let me share this with you. Okay, so here are the two surfaces. So there's that, right, this bowl shape. Let's just look at that by itself for a second. So without the plane, we've got this bowl shape. Then we add a plane to the mix, and it slices right through there, right? From the side, it's just this little line going right through it. And that curve, right, you can kind of see it from above. There we see that circle, right? When we're looking straight down the z-axis, we don't see the change in elevation, right? If we think of z as being elevation, that change in elevation that we see on this side, we only see the shape, right? Like the shadow it would make on the ground, which is this circle, okay? So if I add in the curve now, Again, we see it as a circle from above, but from the side, we can now see that it is really an ellipse in that plane, right? One of our conic sections. Well, not precisely, but what else? Oh, and then I wanted to show you, we have, here is, let's get some of this stuff out of the way. So now there's just our vector function. Sorry, there's our curve, and now I have this vector function pointing at points along the curve, right? So as I change the parameter, as it runs through several values, it's just pointing at points along that curve. Okay, so again, from this angle, we just see this vector function pointing from the origin to different points. It's like the position vector. If this was some particle traveling around, this position vector would be pointing at it as it went, right? So that's that example. I guess that's it for this one. Thanks, everybody. I will see you next time.